Hi guys, today we are into another section in the simple harmonic motion which we discussed in the previous video. The damped harmonic motion. When we consider a helical spring which is attached to a roof or a ceiling and having a mass simple m which is attached to it, this particular mass can move up and down or oscillate in a region. In our previous scenario, we discussed the ideal situation where the total energy of this particular mass or the oscillation would not change. But here, we consider the real life situations. So, in the previous section, the amplitude was a constant as the amplitude doesn't change in the ideal system. But in the real life, we have air resistance as well as frictional forces embedded to this particular mass simple m which is oscillating. So this particular mass cannot move freely. So the amplitude of this particular mass would decrease eventually with time. This is because by the conservation of energy, we know that the total energy is equal to kinetic energy plus the potential energy. Here, by the conservation of energy, this kinetic energy as well as the potential energy would eventually convert to thermal energy. So, with this conversion of energies, we can see that this particle or the particular mass would stop eventually after oscillating. We can see a damping force associated with this particular mass. So we can take this damping force to be equal to minus B times V, where B is the proportionally constant whereas V is the normal velocity we consider. We can consider this oscillation to be a periodic motion as well. Now we apply F equals ma to the particular mass. When we apply F equals ma, we can see minus kx, where k is the spring constant and x is the displacement, or the spring constant can be said as the stiffness factor. Minus kx minus b times v is equal to ma, where ma is the acceleration. Now when we take these particular terms to one side, we can further simplify this equation down in a way where ma plus bv plus kx is equal to 0. Now we have stated the equation after the simplification. So we know that the displacement would be x and the first derivative of the displacement would be the velocity and the second derivative would be the acceleration. For our convenience, we would add these particular terms inside this particular equation. So the first derivative we can take as x dot and the second derivative we could take as x double dot. When we add these terms to the particular equation, we can simplify it further down to x double dot plus b over m x dot plus k over m x would be equal to 0. Now we can take new terms for this particular b over m and k over m. You would take this b over m as 2 gamma, whereas k over m as omega naught squared. The equation we have obtained here is the equation of motion. So this is termed to be equation of motion. The equation of motion is now x double dot plus 2 gamma x dot plus omega naught squared x, which is equal to 0. Now we can take this particular x term to be a e to the power pt, as the first derivative x dot would be equal to a t e to the power pt, and the second derivative x double dot would be equal to a p squared e to the power pt. Now the x dot and x double dot terms could be simplified down as shown here. We'll apply these solutions into the equation we obtained before. So the equation we obtained before will be further simplified down to t squared x plus 2 gamma px plus omega naught squared x, which is equal to 0. We know that this particular x term would be cancelled off. So we would be obtaining p squared plus 2 gamma p plus omega naught squared, which is equal to 0. From the formula we can obtain that p is equal to minus 2 gamma plus or minus 4 gamma squared minus 4 omega naught squared, the square root over 2. So we can simplify this particular terms down, and we'll obtain that p is equal to, moreover, minus gamma plus or minus square root of gamma squared minus omega naught. So these solutions can be applied for the damping motion. The case 1, we take that gamma squared is greater than omega naught squared. In the second case, we take gamma squared is equal to omega naught squared, and in the third case, we would take that gamma squared is less than omega naught squared. So these are the three cases in order to solve the equations. Now this solution is said to be over damping. This is said to be critical damping. And the final solution is said to be over damping. So these are the damping scenarios we can obtain from this particular equation. Here we consider the underdamping situation, which is the case 3. So in the underdamping situation, gamma squared is less than omega naught squared. So in this case we obtain that T is equal to minus gamma plus or minus gamma squared minus omega naught squared, the square root. As we know this term should be minus, we can take the minus omega naught squared term out as minus gamma plus or minus omega naught squared minus gamma squared. So none of these terms would be different from the terms we have before, because here we have a negative term and that negative term would be taken out here. We can apply the complex number rules and see that minus gamma is plus or minus I times this particular term we can take as omega. So the term omega would be equal to omega naught squared minus gamma squared, the square root. As we have obtained this solution, we know that the displacement x we obtained was a e to the power pt. We can further see this a is the amplitude, so we can take a new term for x, which is equal to c e to the power minus gamma plus I omega times t, as well as d times e to the power minus gamma minus I omega times t. After further simplification, we can see that this term of e to the power minus gamma t could be taken out. C e to the power I omega t plus d e to the power minus I omega t. So the solutions we obtained from here could be taken down similarly to a e to the power minus gamma t times cos omega t plus psi, where psi is the phase angle. And this is the oscillatory part of the particular equation. And here we have the amplitude. Let us compress the data we obtained before to the following curves. As we can see, there are 4 curves associated here in the displacement time graphs. The black curve, which is the without damping situation, is normal simple harmonic motion we consider without any resistance. Here we can see the overdamping scenario. The mass would come to rest eventually after oscillating for a period of time, but this oscillation wouldn't be quick enough as the next scenario, which is the critical damping oscillation. In critical damping oscillation, particular mass could come to rest or the equilibrium position is obtained really quickly and in a fast way. Also, we can see the underdamping situation. We can see a curve which is decaying. This is because the equation we obtained for the displacement was x equals a e to the power minus gamma t times cos omega t plus psi. This was the equation we obtained for the particular situation where underdamping scenario is taking place. The curves as shown here will give us without damping, overdamping, critical damping and underdamping situations. So this is it for damping. Thank you for listening.